our schedule has a series of 4 o'clock lectures that are not on the scientific or technical questions that focus so much on the topics, but are some of the broader issues related to renewable and sustainable energy. Today I'm happy to say we have Dr. Chuck Kutscher from the Renewable Energy Laboratory joining us. Dr. Kutscher has a doctorate in chemical engineering from the University of Colorado Boulder. He's principal engineer and group manager of the Thermal Systems branch at the National Renewable Energy Laboratory. So he leads a lot of their work in solar thermal technology. But he's actually here to talk about, as you see, climate change.
Okay. Thanks, Paul. Can everybody hear me okay? Mic in the right place? Okay, good. Well, good afternoon. I'm sure you guys are probably ready to head to dinner. Yeah, I guess we need to turn the lights out. I'll work on it. So let me give a little bit of background. Okay, so as Paul said, I manage the thermal systems group. Most of the people in my group do concentrated solar power research. And that's the area I've done research in for many years. And Carl Koval, who helped organize this, Professor Koval, had contacted me and asked me if I'd give a talk on concentrating solar power. And I said I could, but I'd rather give a talk on this topic. This is a topic a lot of people don't like to talk about because it has become so politicized. But I think it's really the kind of the elephant in the living room. It's the thing that's there, and people walk around it and try to ignore it, but it's still there. So I got interested in this subject back in 2000, 2001. As a volunteer, I was the chair of the American Solar Energy Society, and when I took on that role for a couple of years, you write a column in the magazine, the Society magazine called Solar Today, and I thought, well, I've been spending all my life doing research. I need to get more informed about broader topics. And as I looked into that topic of climate change, it really dawned on me how important it was and how misunderstood it was. So back in 2006, we had a conference in Denver. And at that conference, I asked experts in the different areas of renewable energy and energy efficiency to do sort of a bottoms-up study of what they thought we could do in the U.S. to reduce carbon emissions by 2030. And it resulted in this report that came out in 2007. It was released on Capitol Hill in Washington, D.C., Tackling Climate Change in the U.S. I'll talk about this a little bit at the end, and I'll pass it around for you guys to take a look at. But after this report came out, I often gave presentations where I'd kind of give background on climate science and then talk about the solutions. And in one of those presentations, our local state senator was there, and he came up to me afterwards and he said, Chuck, I'm doing this workshop at the state capitol, and I keep getting all these skeptics giving me all these arguments against climate science. Could you put together a specific presentation addressing skeptic arguments? And I did that, and I've been giving a presentation like that since and updating it. It's hard to keep up with all the skeptic arguments, but I try to keep up with them. And so I am going to give a presentation that basically focuses on that. I will conclude by talking just a little bit about the solutions, because you don't like to tell people, hey, we have this big problem, and leave them without solutions. And in fact, there are solutions, and I know you've been hearing about many of them in this workshop. So this is not a title I came up with. Carl said, well, let's call it Climate Change Still a Driver for Sustainable Energy, question mark. It's sort of telling that we would, in this day and age, have a title like this. And actually, I think the best publication that summed up this situation was The Onion. Did any of you read The Onion? So I'll show you a headline out of The Onion later. They really do a good job of capturing this. Before I get into the climate science, I just wanted to spend a few slides on the energy problem. I was down at the Mountain Film Festival in Telluride, and they had this symposium before it. It's held every Memorial Day weekend. And they asked me to kind of give an overview of resources, renewable resources versus fossil resources. And just ignore you? Yes. What happened? You were ringing. I think I can talk without slides. but anyway, so it was actually, the subject was population growth, but they said they wanted me to talk about what's happening to resources. And the bottom line of what I said is that, well, yeah, I mean, there are finite fossil resources, but the renewable resources are really far from what we would consider finite. Okay, thanks. So I guess to put things in perspective, if you step back enough, you'll realize that this age of oil consumption that we're in is like a blip in humanity. It's a couple hundred years, okay? So this is an odd situation we're in right now. It's not going to last forever. You know, recently with the worldwide recession, the price of oil has actually dropped a little bit. But in any case, you know, this is the oil age is a temporary age. What we're really seeing is, of course, we have this population growth problem. We're at 7 billion people right now. But the real population problem is the population we already have, okay? You know, we passed our highest growth rate of population back in the 1960s. It's been declining since then. Not that population growth still isn't a problem, but the biggest problem we have is the people we have here already and the fact that they're trying to improve their standard of living. So, you know, we don't know there's different thoughts about what's going to happen to the population growth. I don't have that curve here, but it could level out at 9 or 10 billion, you know, different theories about what it'll level out at. But one thing we know is that the developing nations are going to be using more and more energy, and the type of energy they use is very, very important. So one of the things is, you know, we talk about energy security, right? Well, we got this problem with imported oil. That's been dropping also, by the way, you know, where we actually have increased oil production domestically. But, you know, if we really just had a problem with imported oil, we could do what the Germans did during World War II. We could convert coal to liquid fuels. That's the worst thing to do from a climate change standpoint. So that's one of the reasons it's important to get climate change. Similarly, with the oil sands or tar sands in Canada, there's a lot of energy intensity that goes into producing this oil. So again, from a climate change standpoint, climate scientists point to this as being the worst thing we could be doing, and that is going to unconventional forms of fossil fuels. You might have heard that you know, gas prices have really dropped. I'll show that in the next slide. But these are gas shales throughout the U.S. What's going on? Anybody? Has this happened before? What's that? Turn the wireless off? Really? Oh, okay. I see what's happening. Yeah, I got you. Okay. Oh, sorry about that. Give me a second here. Turn the Wi-Fi off. This is the one I was at, right? Okay, I see what's going on. Okay, so there's a lot of gas shale. This has caused a significant drop in the cost of gas in the U.S. And this is really interesting. This is from the Energy Information Administration. You know, coal for the longest time was providing somewhere between 45 and 50% of U.S. electricity. Coal, as you probably know, is a big problem in terms of carbon emissions. Natural gas, if you produce electricity in combined cycle natural gas plants, and you don't account for fugitive emissions and those kinds of things, gas electricity might have about half the carbon emissions of coal. And so this is really significant that in the last couple of months we've reached the point where coal electricity has dropped to the level of natural gas electricity, both around a third of U.S. electricity production. So that's a real significant change that coal has dropped that much. You may have read stories about coal mines being shut down, coal miners going out of work. This is a really big change. You've probably seen the coal industry advertising like crazy on TV to prevent the EPA from coming out with carbon emissions rules. And so what you see in the U.S. right now is natural gas is really, really cheap. And so we're seeing more natural gas burning. Again, under the best of circumstances, you have half the carbon emissions from natural gas than you have from coal. So natural gas is good in terms of helping to enable variable resources like the sun and like the wind. But it's not a permanent solution to climate change by any means. Also, you can see the prices abroad are much higher than in the U.S., so it's unlikely that these prices are going to stay this low for that long. And finally, before I move into the climate change in particular, I would ask this question. Well, you know, we burn up fossil fuels to produce energy. Is there anything else we can do with fossil fuels? And this is a photograph taken out of a National Geographic magazine on energy. And this family, they brought out all the products that's in this family household that are made from fossil fuel. So the point is that with fossil fuels, you can make incredible numbers of recyclable products that can be used for generations to come. So do you really want to take carbon that nature has naturally sequestered in the environment, bring it out and just burn it up so that it's only good for our generation, we're depriving future generations of it? Or does it make more sense to use it in a recyclable way? And I would argue, of course, the latter. Okay, but the big challenge of our time is climate change. So I'm going to go into some of the arguments here. You're probably familiar with the basics of climate change. Basically, essentially what's happening is we're adding carbon dioxide to the atmosphere from burning fossil fuels. And carbon dioxide is a very strong absorber of infrared radiation. So the Earth wants to be in balance. It's got shortwave solar radiation coming in. It emits, like any object that's above absolute zero, it emits infrared radiation out to space. Those two want to be in balance. Right now, the Earth is not in balance. It's probably got about 0.6 of a watt per square meter more coming in than it has going out. I mean, that sounds like a lot, but there's a lot of square meters on the surface of the Earth, right? So that's the problem. Right now, there's more coming in than there is going out, and the only way that the planet can get back into balance is to heat up so it's emitting more radiation out to space. So this carbon dioxide is adding to the natural greenhouse blanket in our planet. It's making things hotter. So if you look at carbon dioxide, and this has been taken since 1958 on the top of Mauna Loa and on the Big Island of Hawaii, you can see it's been going up steadily, and it actually tends to breathe with the northern hemisphere where there's more vegetation. And we're right now, today, like 395 parts per million. Now, for basically 800,000 years, at least, probably millions of years, the CO2 content of our atmosphere varied between about 200 parts per million and 300 parts per million. It's now pushing 400. It's gone up enormously, okay, just since we started burning fossil fuels. I point out to people that I was born in the middle of the last century, 1950, and the air we're breathing in this room today has 25% more carbon dioxide in it than the air that I first breathed the day I was born. I mean, within one human lifetime, to increase a fundamental constituent of the atmosphere by 25%, that is an enormous change. And again, CO2 is a very important trace gas in the atmosphere. So what you see is, if I went over to Barnes & Noble, I looked at books, you see all these books saying, oh, climate change is a joke, it's a hoax, etc. This was a billboard put up by the Heartland Institute in Chicago a couple months ago. I still believe in global warming. Do you? This is Ted Kaczynski, the Unabomber. I don't know if any of you remember the Unabomber story, but we can go into that. He's a bad guy in prison, and apparently he's a mathematician, and he believes that we're causing global warming. So if you believe we're causing global warming, you must be something akin to the Unabomber. They got such bad PR on this thing that this billboard was taken down after about 2 days. You might have heard a couple years ago that some emails were hacked from the Climatic Research Unit in England. Climate scientists there, their emails were revealed. What those emails really showed, they tried to make a big deal out of this, like it showed that the scientists weren't being honest with the public. What the emails showed was very frustrated climate scientists saying to each other, how do we get this message out? How do we get people to listen to us? That's really what came out of those emails. And so there's a lot of press about this, about these emails. What you didn't see in the press is the results, and I'll show that later, but I just wanted to point this one thing out before we go on to that. If I wanted to ask all of you, if I wanted to guess what your opinion on climate change is, I probably wouldn't ask you how much physics you've had or how much atmospheric science you've had. I'd probably ask you whether you're a registered Republican or a Democrat or an independent, and that would be the best indicator. That's pretty weird. It's something that's basically a scientific topic. So you can see here, percentage of people saying global warming is exaggerated, 22% of Democrats, 44% of independents, 66% of Republicans. Why is that? It's because these different people get their news from different sources, and people tend to listen and watch news that reinforces their opinions. I won't get into this whole, I'll show you a book later that gets into some theories about this, but I'm not going to really delve into that. But I mentioned that issue with the climate gate. There were three separate, I won't go into all these quotes, you could read them yourselves. There were three separate British panels that completely vindicated those scientists. And this is what they concluded, those 3 separate British panels. This didn't make much news. Right? The big news was about, oh, these scientists are deceiving us. This really did not make the news. Now, here's what the Onion says. Report, global warming issue from 2 or 3 years ago may still be a problem. I mean, it's pretty weird when we're living in a day and age where our comedy sources get closer to the truth than the news does. Okay, I want to go through some of these skeptic arguments. I can't go through all of them. At the end, I'll give you some sources if you want. If somebody says to you, hey, it's not happening because of blurb, okay? I can't cover everything, but I'll tell you where you can get that. So I'm just going to cover some typical ones. So these arguments fall into different categories. So one of the categories is, well, it's not happening. You know, well, the Earth is getting cooler. It's not getting warmer. Heard that one, right? So here's some things you see. It was warmer during the medieval warm period, which, 1100, 1200. And the other one is the Intergovernmental Panel on Climate Change has dropped Michael Mann's hockey stick curve. What's the hockey stick curve? It was a study of northern hemisphere temperatures going back 1,000 years that shows a very, very sudden rise in temperatures as we start burning fossil fuels. It's called the hockey stick because it has a sudden upturn. The skeptics hate the hockey stick. You'll see all sorts of stuff saying the hockey stick is bogus. I get a kick out of it. I've seen this over and over again, this medieval warm period warmer than today. But what I really get a kick out of it, if you look at that, here's 1800, there's 1900. What's this, 1950? It doesn't even go to today's time, where we've seen most of the carbon emissions and most of the temperature rise. Okay, so let's answer those two. What's the scientific reality? Well, there was so much of a hoopla over Michael Mann's hockey stick curve that Congress asked the National Academy of Sciences to study it. And they put out a 160-page report after they studied it in detail. Here's what they concluded. This is right out of the National Academy report, okay? Here's Michael Mann's hockey stick. It's the red one here, and it upturns. And they have all these other hockey sticks. I mean, not only did they verify Michael Mann's hockey stick, but they had all sorts of other hockey sticks. So these are based on, when you go back in temperature, you don't have a good measurement of the temperature, right? So you have to use tree rings, borehole readings, glacier lengths, various things. So these all use different proxies, different substitutes for the actual measured temperature. But you can see they're all showing this upturn. They said the committee finds it plausible, and the National Academy of Sciences always has to understate everything, right? They're a group of scientists. Finds it plausible the Northern Hemisphere was warmer during the last few decades of the 20th century than during any comparable period over the preceding millennium. Well, what about this thing that the IPCC was so embarrassed by the hockey stick curve that they dropped it out of the latest report? I guess these people don't actually open the volumes. This is page 467 of volume 1 of the last IPCC report, 2007. And here are the various hockey sticks. Not quite the same as the National Academy, but again, all the hockey sticks, including Michael Mann's. I'm going to pass this around. So what's the IPCC, the Intergovernmental Panel on Climate Change? It's a group of scientists, and about every 6 or 7 years they come out with 3 volumes. And volume 1, each is about 1,000 pages. Volume 1 is called the Physical Science Basis. So they've been doing this since 1990. There'll be another report coming out next year. So this is 1,000 pages. Now this is not original research. What they do is they go through the peer-reviewed literature. I'll pass this around. I want people to get an idea of the weight of the evidence. Literally. Pass that volume around. It's 1,000 pages. What it is it cites the peer-reviewed scientific literature. It's not original research. So just by citing and summarizing peer-reviewed literature, they have 1,000 pages here. And if all this information on the hockey stick wasn't enough, the Journal of Climate in May, just last 2 months ago, basically an Australian group came out with an Australian hockey stick. So you see that in the Southern Hemisphere as well. So what's happening to the temperatures? There's various groups that measure the temperature. This is the air temperature near the surface of the Earth. Annual temperature average for each year. And you can see it varies around. The red line is the 5-year running mean. And you can see in general it's going up. There was a period here from 1940 to 1970 1970, where we were burning so much fossil fuel during World War II and shortly after that, that sulfate aerosol emissions, scientists believe, were causing a masking effect and reducing the solar output. And so there's this sort of flattening. But eventually, 1970 in the US, we passed the Clean Air Act, and enough CO2 had built up that this temperature really started marching up very seriously. So that was the Goddard. This is the British data. This is from NOAA in the US. These are two satellite measurements as opposed to surface measurements. They also show basically the same trend. It's getting hotter. Now, there's going to be some natural variability, and these things, El Nino Southern Oscillation, that's this variation between El Nino and La Nina. In the Pacific, El Nino means warm surface waters. In the Eastern Pacific, La Nina means cooler surface waters. That variation in and out of El Nino and La Nina certainly has an effect. Volcanic eruptions, again, cause some solar dimming, and also there can be solar influences. So this particular paper in Environmental Research Letters, just this last December, attempted to filter those things out, and you can see from 2000 to 2012, a definite trend here in rising temperature. Here's another one. You say, well, you know, they put these thermometers out there, and then they build cities around them, so of course they get warmer. That's called urban heat island effects. And what we're really seeing is not an increase in the surface temperature of the Earth. We're just seeing the fact that we're urbanizing. Now, a lot of studies have disproven this. I don't have time to go into all of them. I just got one here coming up. This is urban versus rural stations in China. Now, if you want to pick a country that's urbanizing at an incredibly rapid rate, it's China. So this is sort of like a worst case scenario. And if you compare urban stations to the rural stations, it's hard to tell them apart. They're all showing this increase from 1980 to today. And also, where is it getting the warmest? It's getting the warmest at the poles. All right, the Arctic is really warming up. That's not due to urban heat island effects. There have also been studies that look at cities, and they look at windless and windy nights. All right, so if there was a heat island effect, you'd expect when there's no wind, that would really affect the temperature. They say very little difference between windy and windless nights. Here's another one. In that report that I'm passing around, the IPCC lowered their predictions of sea level rise for 2100. You know, well, they realized they were wrong and they were exaggerating, so they lowered them. So what's the truth there? There's a little bit of an element of truth to the fact that they lowered it. In 2001, sort of the worst case projection for 2100 was 0.9 meters. In the 2007 report, 0.6 meters. So why the decrease? Well, basically in 2001, they tried to estimate what are called ice sheet dynamics. I'll show you a photo of that in a minute. In 2007, they said, you know, we're under so much criticism, let's really put some probability and statistics on this, and let's assign risk categories. And if we can't really model something accurately, let's not even estimate it at this point. We'll wait until we can model it accurately. So they were a lot more conservative in 2007. So the 2007 report did not include these estimations of ice sheet dynamics. So if you look through the IPCC reports, you'll see statements that say they couldn't estimate with high certainty future rapid dynamical changes in ice flow. Now, I've taught heat transfer here at the university. I've taught to seniors and to graduate students. How many of you have had a heat transfer course? Do we have any MEs in here, and most of you physicists? We have a few. So if I take an ice cube, and I put an ice cube on this table, and I ask my students to estimate how long it will take for that ice cube to disappear, and they can figure the heat being conducted in from the table, natural convection with the air currents, radiating to the ceiling, right? They can estimate within maybe 15–20% how long it'll take that ice cube to melt. That's not what's going on with our ice sheets. What happens is, these puddles form on the surface. Those puddles now are darker and absorb more solar radiation, amplifies the effect. Eventually, those lakes that are formed can suddenly cause what's called a moulin and actually drain to the bottom of the ice sheet. And these ice sheets, if you go to the highest point in Greenland, you know, this is basically 2 miles thick. And this water can suddenly burrow its way down 2 miles. You don't want to be in a kayak on one of these lakes when it suddenly drains. It can be a pretty scary proposition. Anyway, so what happens is, once this water starts to flow, you have very, very different heat and mass transfer effects going on. It's much more complicated. They haven't been able to model it really accurately yet. But anyway, we know sea level is going up. What are we going to see in 2100? Some estimates are as much as 6 feet. There's a new study that just came out in the last month that it looks at 14,000 years ago. There was a point where sea level was going up about 1 meter every 20 years. But a very interesting model of the ice sheets that existed and what happened then. And so I don't know that we can say that that would happen again. Things are different today. Some people argue CO2 is so high, this is really going to accelerate due to positive feedbacks. But I would say most scientists would say probably in the neighborhood of about 3 feet of sea level rise or so by 2100 is probably what we're in for. So here's Florida. And there's Florida with 1 meter of sea level rise. You can see it's an obvious big impact on the state of Florida. It's a big impact on any coastal cities. There's about 100 million people that live within 3 feet of sea level. That's a huge number of people, and even more people rely on agriculture in river deltas that are close to the sea or within 3 feet of sea level. And of course, that agriculture would be ruined by salt water. In the case of Bangladesh, a 1.5 meter sea level rise would cause 17 million people to have to leave. And a big impact. Here's another one. The IPCC was wrong about Himalayan glaciers disappearing by 2035. This is one of the other 2 volumes, not the one I passed around. There's another statement, for every retreating glacier, there's an advancing one. So I want to respond to these 2. This was actually a mistake in one of the volumes. And I was involved in an International Energy Agency task once, and we put out reports. And I can tell you, if we had one mistake in a 1,000-page report with an international committee working on it, we were doing really well. But they shouldn't have made this claim because the low glaciers in the Himalayas are disappearing. The very, very highest ones are so high that it's going to be a while before they really start melting. So they corrected that, they apologized, they made that correction. But let's take a look at these things. What's the scientific reality? Well, with all the hoopla that the IPCC shouldn't have said that all Himalayan glaciers could be gone by 2035. They will, by the way. The USGS predicts all the glaciers in the U.S. Glacier National Park will be gone probably by about 2025. Right? So we're only talking about 10 to 15 years before all those glaciers are gone. But they're at much lower elevation. But anyway, look, here's the East Rongbuk Glacier on Mount Everest, August 1921. Here it is, October 2008. What a dramatic change. And you can see these pictures all around the world. So one of the skeptics in his book says, for every glacier retreating, there's an advancing one, but the press doesn't tell you about that. Well, the World Glacier Monitoring Service basically keeps track of glaciers. They have records that go back to the 1880s. This is 1885 here. And basically, the blue bars, here's 1985, here's 2005. The blue bars are advancing glaciers, and the red bars are the number of retreating glaciers. So basically 90% of the world glaciers are retreating. Of the ones that are advancing, most of those are in the South Island of New Zealand, and the actual ice mass is dropping because they're thinning faster than they're advancing. They're still losing ice. Here's glacier mass around the world. These are similar curves. One is reference glaciers and the other is all glaciers. But essentially, you can see glacier mass is going down and it's concave downward. That is, it's accelerating. There's a National Geographic photographer and mountaineer, Jim Balog, who lives here in Boulder. And he has a website called extremeicesurvey.org. How many of you came in through Denver International Airport? Did any of you how many of you took the train to get here? Any of you noticed a video by the train of this ice events going on? That's Jim Balog's stuff. He puts Nikon cameras all around the Arctic. He has them take a picture once a day, and he puts frames together. He's also done some video. So this is a video. There was a special NOVA show on his work about 2 years ago. If you can catch it, they often repeat it. You should look at that. And there's a new film out called Chasing Ice, which is all about what Jim Balog does. And it just won, I saw it down at the Mountain Film Festival in Telluride, and it won Best Cinematography at the Sundance Film Festival. and it's going to be released this fall. And the director is a very young director from CU Boulder. He really did an incredible job. So keep an eye out for Chasing Ice. But this is a video camera that they had set up on June 9, 2007, and there's no sound with this, and it's speeded up a little bit. But he superimposed the U.S. Capitol building to give you an idea of the scale of this event. So take a look at this. I think hopefully this will play. And if you've been to the U.S. Capitol, I think you'll agree it's a pretty big building. Anyway, if you see Chasing Ice, the climax of the movie, I guess it's okay for me to tell you the climax of the movie. Basically, they had video cameras set up because they were expecting a big glacier calving event. And they waited weeks and weeks, and it didn't happen, They were about ready to pack up and leave. And all of a sudden, they picked it up. And it's a glacier calving event that's the area of Manhattan Island and 3 times the height of the Empire State Building. And they have a film clip of that in this movie. It's pretty amazing. Skeptics say, okay, all right, the Arctic is losing ice, but what about, the Antarctic? That's getting colder. You don't talk about the Antarctic. It's gaining ice. What's happening down there? A number of ice shelves have broken up. These ice shelves extend out over the ocean and they float, so when they break off, they don't add to the sea level rise because they're already floating and displacing water. But anyways, this is one that broke off in March 2002. This is the Larsen B ice shelf. This is about the size of the state of Rhode Island. There are other, the Wilkins ice shelf broke off about a year ago. That was also very large. But what happens, what they think is happening is, warm ocean water is undermining these ice shelves, and that's what's causing them to break off. But the problem is, these act like a cork in a bottle. So the land-based glaciers, which do add to sea level rise, they're held back, and they start moving toward the ocean a lot faster. So in the case of the Larsen B ice shelf, one glacier started moving at 510% faster, another 400% faster. So that's the impact of these ice shelves breaking off. In terms of this ice mass, are we losing ice in the Antarctic? Because, in the East Antarctic, you'd argue that it's sort of neutral. The West Antarctic is losing ice. So what's the net effect? NASA has a pretty cool way of determining ice mass. And what they do is they have these satellites they're called the GRACE satellites. The G is for gravity in this. And they do measure gravity. There are 2 satellites in polar orbit. Okay? So if you have 2 satellites in polar orbit, they go around the North and South Pole. And what happens is they have basically a Doppler measurement that measures the distance between these 2 satellites. All right, so from one satellite they can tell the difference in the next one. Well, what happens when the first satellite goes over a more massive area, it speeds up and the satellites get further apart. They can map out the gravitational pull just by measuring the distance between this pair of satellites. So when they do that, if you look at the main ice sheet in the north, that's the Greenland ice sheet, and the whole of the Antarctic ice sheet, you can see they're both declining. The Greenland is obviously concave downward, and there's a slight concavity downward of the Antarctic ice sheet. So contrary to what the skeptics say, we're losing ice at both poles. There's also some dangerous feedbacks. As we lose forests, of course, forests remove carbon dioxide from the atmosphere. And so as climate change impacts those, and of course deforestation is a big effect, that causes a problem. Also, this melting permafrost. You've probably seen villages in Alaska relocated because of melting permafrost. You've seen roads buckle, that sort of thing. Well, this permafrost, has frozen vegetation in it. And when that permafrost melts, that vegetation starts to decompose. Now, one of the estimates is that in some places, 30% of the emission won't be CO2, but will be methane. And methane has about 25 times the impact of carbon dioxide in terms of being a greenhouse gas. So methane is a very powerful greenhouse gas. So what happens if you look at some of these lakes in the wintertime, if the permafrost is melting, the decomposing causes methane release. The methane gets trapped under the ice. In the summertime, it will bubble to the top and just enter the atmosphere, but it gets trapped under the ice. So one professor from the University of Alaska has been going around really monitoring what's going on with these methane releases. And the next clip is just her drilling a hole in the ice, and you can see what happens.
Oh my God.
Okay, so that's basically methane, the key component of natural gas, coming out of the decomposing permafrost. Some scientists are very, very concerned that this is a ticking time bomb, and that is that we could reach a point where there's a tipping point and there's a massive release of methane into the atmosphere, along with carbon dioxide. If that happens, global warming would greatly, greatly accelerate. Yeah?
What's the current level of methane in the atmosphere? Parts per million?
In parts per million. It's, I'm going to show you well, no, I guess I have the radiative forcing. I don't know that number, but I'll show you a chart from the IPCC that actually gives you the radiative forcing of methane versus CO2. We can look at that, which is really the important thing you want to know. Okay? CO2 right now is more important in the atmosphere than methane because there's more of it. The other thing is hard to compare too because methane has a much shorter life than CO2. CO2 can be around for 500 years. I mean, it decays rapidly in the beginning, whereas methane it decays much more rapidly. So it's hard to compare them. But in general, they argue about 25 times the global warming potential of CO2. Okay, so what the next set of arguments is, okay, climate change is happening, it's warming, but we're not causing it. One of these is we're coming out of a little ice age. Well, there was a little ice age a few hundred years ago, but we know what caused it. It was reduced output from the sun and also aerosol emissions from a period of significant volcanic activity. And so if you look, at this period, there was definitely a period of reduced solar output. All right, so we can explain that. And so really, if you look at what could be causing climate change other than us, you have to look at the variation in solar output. Now we know it varies in 11-year sunspot cycles, and that has a slight impact on the temperature. But there can be longer-term effects on the sun. So what's the reality there? Well, for one thing, these things have signatures. You can look at, what would happen if the global warming was caused by greenhouse gases in the atmosphere trapping infrared radiation versus what would happen if it was due to increased solar output. Okay? So basically, essentially, greenhouse gases warm the lower atmosphere, but because they trap that heat low, the upper atmosphere cools. If it was the sun increasing, you get more solar energy absorbed throughout the atmosphere. So you'd expect both to go up. And what do we see? We see the lower atmosphere warming and the upper atmosphere cooling. This is the fingerprint of greenhouse gas warming, not the sun. Similarly, if it's the sun, you'd kind of expect the sun to have a bigger effect when the sun is shining, which would be during the day. But in fact, we see warm nights going up faster than warm days. Okay? So, what can keep the nighttime temperatures warmer is trapping infrared radiation. Again, greenhouse gases. But the best way of all is if we look, here's the temperature going up, and here's solar output. It was going up during the first part of this century, all right? But you can see that over the last 30 years, it's been going down. All right, so the Earth, if it wasn't for us, the Earth would be cooling slightly over the last 3 decades. And here's the chart I was talking about. So these are the radiative forcing components. So here's carbon dioxide, which is causing warming. Here's how much methane warming is caused by methane. So here's how the radiative forcing components compare between CO2 and CH4. All right? And you can see that aerosols, air pollution, volcanic emissions, that sort of thing, would cause a negative effect. Although all this is just anthropogenic. This is what we're causing. So down here, this is the solar effect. Now this goes back to 1750. If it just went down for the last 30 years, that would show a negative effect from the sun. But because this goes back to 1750, there's a slight net positive effect from the sun. All right? This is the total net anthropogenic effect, which just swamps out the solar effect. Okay? So when people say to me, look, I mean, mankind isn't causing all the climate change, all the global warming, is it? And I say, no, it's not. It's only causing 90% of it.
Excuse me.
Yeah.
Why aerosols have negative?
Why do aerosols have a negative effect? Because of the solar dimming effect. Basically, when you have, back in 1991, when Mount Pinatubo erupted, okay, in the Philippines, we saw the output of solar power plants in the desert go down significantly for the rest of 1991 and most of 1992. And that's due to these sulfate aerosols. The sulfate aerosols basically cause a masking effect. This is important. Have you ever heard of geoengineering, ways that we can counteract global warming? One is to inject lots of sulfate aerosols into the stratosphere. Very dangerous stuff. For one thing, it wouldn't do anything about all the CO2 that is absorbed in the oceans and causing the pH to drop, the acidity to go up. For another thing, it could cause acid rain. It would change precipitation patterns around the world. And also, it's just covering up the problem. It's not solving the problem. If we ever had a worldwide depression or war or something, and we stopped this expensive program of injecting sulfate aerosols into the stratosphere, all of a sudden we'd have tremendous warming. But that's one of the methods that have been suggested, is mimic volcanoes and inject sulfate aerosols into the upper atmosphere. Okay, El Nino. All right, this is from NOAA. This goes back to 1950. So here's 1992 to 2012. Essentially, El Ninos are this positive surface temperatures in the Pacific, sea surface temperatures, and negative. You can see that 2010, 2012, we had a double La Nina going on. All right, that's really been trying to keep the planet cooler because of this. The other thing that's keeping the planet cooler is all the coal burning that's going on in China. If China gets serious about cleaning up its carbon emissions in coal because of its health problems, we're going to see global warming go up faster, because right now it's being somewhat masked by all the pollution that the Chinese coal plants are putting into the atmosphere. But anyway, so here's the El Nino, La Nina effect. You see, if anything, for the last 5 years or so, we've been in much more of a La Nina situation, a cooling situation, than a warming situation. It's clearly not El Nino causing this. There hasn't been enough of them. There was a big one back in 1998. But the other thing is that these are periodic events. All it does is it takes ocean heat, puts it into the atmosphere. All right? And then it goes back into the ocean. It goes back and forth. If you look at the total sum of how much energy we've added from greenhouse gases to the ocean versus the atmosphere, this is what you get. This is from a paper by Church et al. Geophysical Research Letters back in September 2011. This is all the energy content we've added to the ocean. This is the atmosphere. The oceans hold a lot of heat. So obviously it's not El Nino, because if that were true, the ocean would be getting cooler too. And these are just a study done by Scripps showing that, in fact, not only are ocean temperatures going up, but if you look at the profiles with depth, again, the fingerprint of greenhouse gases is there. The way the oceans are heating up is consistent with the greenhouse effect. This is just July 8th, all right? This is just a week ago. U.S. official, in this case it's Jane Lubchenco, who's head of the National Oceanic and Atmospheric Administration, was at a conference saying, higher ocean acidity is climate change's evil twin, major threat to coral reefs. Now, we're already seeing a lot of coral death for a lot of reasons. Some of it is fertilizer runoff, but a lot of it is elevated sea surface temperatures. It was a huge die-off of elkhorn forest in the U.S. Virgin Islands because of elevated sea surface temperatures. So now we're into the situation where dissolved CO2 is causing the pH to drop. Ocean acidity is not going to allow calcium-based animal life to form, and will in fact dissolve it. Now here's another one. You've probably heard this one. If you look at the ice core record that goes back 8,000 years, the argument is that it's these changes in the Earth's orbital parameters that bring us in and out of these ice ages. And that causes a change in the solar distribution and a change in the temperature. When the temperature goes up, CO2 comes out of the ocean. All right? Now what scientists have said, yeah, that's true, but as the CO2 comes out, it's a very positive feedback. It allows these big temperature swings that we see between ice ages. But there's a very interesting new paper that just came out in last let's see, when was it? April 5th, so 3 months ago. Here's from the ice core record. Now this is just going back 22,000 years, but essentially these yellow dots are the carbon dioxide that we measure in the bubbles when we drill down for these ice cores. And the red is the temperatures that are inferred at the time those air bubbles were deposited in the ice. This is in Antarctica now, okay? And this is by proxy. They can basically infer from the oxygen 18 isotope concentration what the temperature would have been. That's a pretty well accepted procedure. And you can see here, this is what's been reported before, that the temperature goes up and then the CO2 rises afterwards. And so the skeptics say, it's the temperature, not the CO2. The CO2 isn't the driver. Well, a very interesting study. This group came out and said, well, you know what? Yeah, that was the temperature in Antarctica. But what if we try to look at the temperature in the rest of the world from proxy measurements? What if we try to come up with a global average temperature? When we do that, they get this blue line. And the blue line clearly lags the increase in CO2. In this case, the CO2 is driving that global temperature to go up. And so think about, this is where we are. There's a lot of heating already in the pipeline. If we levelize our carbon emissions today, if we stop adding more carbon to the atmosphere, there's still more warming in store for us, all right, because of this delay. Skeptics say computer models are unreliable. This was provided to me by Warren Washington Venkart. He's been a modeler since the 1960s when he was at UCLA. Very famous modeler right here in Boulder. And in the mid-1960s, this is what they could model, 70s to 80s, 90s, 2000, etc. You can see how sophisticated these models all around the world have gotten. They're still working on this one, the ice sheet dynamics that I mentioned. Remember those 4 IPCC reports that I said have come out? All right, here's the 1990 report, 1996, 2001, 2007. This shows you the resolution of those models. My first job out of school was for Sperry Rand. We had twin UNIVAC 1108 computers. We were real proud of those computers. Okay? This Mac book I have right here could kick its butt. Okay? Computer technology has increased tremendously over the last few decades, and it's reflected in greater and greater accuracy of these climate models and good agreement from around the world. Here's a report that shows we take these computer models and we want to try to reproduce what happened between 1900 and 2000. Can we? All right? So the black line is the actual temperature observed. All right? The blue is what the models predict if we leave out anthropogenic man-made effects. Only by including what we've done to the atmosphere do we get the red line in agreement with the black line. Only way the models can reproduce the temperature rise that we've seen in the last century is by including greenhouse gases and aerosols and the other man-made effects. You probably, I don't know if any of you read The Economist, but it's considered a very conservative magazine, all right? Not the people that would jump on a global warming bandwagon, okay? This is from the June 16th issue, so this is what, 2 days ago. There is no serious doubt about the basic cause of the warming. It is, in the Arctic as everywhere, the result of an increase in heat-trapping atmospheric gases, mainly carbon dioxide, released when fossil fuels are burned. So what's the bottom line? Variations of solar output and masking for volcanoes impact climate change, but only human impacts can explain the temperature rise since 1970. All right, here's another argument. It's not bad. Let's take a look at that one. You see what's happening to the temperatures here. This is what we predict for temperature rise in the U.S. by mid-century. Right? We're talking, in some cases, 4 to 5 degrees Fahrenheit. By the end of the century, up around 8, 9 degrees Fahrenheit. These are temperature rises that are enormous. Skeptics say these weather extremes we're seeing are normal. There's been a big change in this lately. I saw this the other day, July 8th, political columnist, longtime climate skeptic George Will. How do we explain this heat? One word, it's summer. What's so unusual about this? Well, This is the number of temperature records, U.S. temperature records, since we started taking data that were broken in June. Those of you who spend time in Colorado know we've had incredible fires going on. Now, there's a lot of things that cause fires, but one thing for sure, when you have a much, much earlier spring, we have very, very dry conditions, okay? And also, when you have bark beetles now surviving the winter and going through 2 reproductive cycles every season instead of 1, and causing those trees to die, you have the potential for hotter fires. We're seeing that. This is a paper that looks at worldwide temperature distributions around the mean, and each of these Gaussian or bell-shaped curves represents a different decade, 1951 to 61, 61 to 71. Here's the point. Here's 2001 to 2011. These bell-shaped curves are marching steadily every decade to the right. So that's what's happening. This average temperature distribution around the world is moving to the right. Where are the records, those high temperature records set? They're right here in the tails of the Gaussian distribution. It's no wonder we're setting all these records, because that whole Gaussian curve has been moving to the right every decade. NOAA just came out with a new report. I just got this off the web July 10th. Drought in Texas, roughly 20 times more likely as a result of the greenhouse effect. U.S. National Climatic Data Center said, during the June 2011 to June 2012 period, each of the 13 consecutive months ranked among the warmest third of their historical distribution for the first time in the 1895 to present record. The odds of this occurring randomly, 1 in 1,594,323. Do I believe they can calculate to that many significant figures? No, but it's a pretty impressive number. The July 2012 issue of the American Meteorological Society Bulletin has a special report explaining extreme events of 2011 from a climate perspective. So we're really seeing a lot of stuff in the scientific literature now that's saying, you know what? We can show these extremes are not natural. Okay, right now there's over 1,200 counties in the U.S. that are considered natural disaster areas because of drought. That's 1/3 of U.S. counties right now are considered natural disaster areas. All the models have predicted that water cycle would intensify. Dry areas would get drier, wet areas would get wetter. That's what the models have been showing. A new report that came out in the journal Science, April 27, 2012, actually went around and looked at sea surface salinity in the drier areas and the wetter areas. Fundamental thermodynamics and climate models suggest that dry regions will become drier and wetter regions will become wetter in response to warming. We show that ocean salinity patterns express an identifiable fingerprint of an intensifying water cycle. This is what we're seeing. This is a quote from the guy who was head of NASA in the last presidential administration. Who's to say today's climate's the ideal one? Maybe warmer's better. Well, we've been around, Homo sapiens have been around for 130,000 years, okay? So why did it take until 8,000 to 10,000 years ago for us to really establish our agriculture and permanent cities? Well, we've been, for the last 8,000 years, in this incredibly stable temperature regime. And in terms of sea level, you look at the Nile Delta, you look at delta areas where agriculture got started. Here's the sea level. It's only when you go back about 8,000 years ago it becomes dead level. Right? Not only is this an incredibly blessed period that's allowed civilization to develop, but all the life on the planet has adapted to this climate. That's what makes it the ideal one, because it's the one that produced us. And yet, this is what we're doing to that stable climate. These are the projections under various scenarios that we can see the temperature rise. Okay, the final argument is, okay, it's happening, we're causing it, yeah, it's bad. But you know what? We can't afford to fix it. $120 billion a year. What's that number? Well, the U.S. National Academy of Sciences did a report in 2010. They wanted to estimate what's the current annual hidden cost of fossil fuel energy in the U.S. So when you look at all the environmental effects, they estimated it costs us $120 billion a year. That's what our fossil fuel economy costs us. $1.9 trillion a year. That's a study by Ackerman and Stanton from Tufts University, the annual cost of the U.S. of climate change damage by the year 2100. A study by Nicholas Stern, who was chief economist of the World Bank, came out with a huge report, estimated the cost of mitigating climate change, changing our energy infrastructure, about 1% of the world's gross domestic product. Okay? The cost of cleaning up the damage, 5 to 20%. He's recently come out and said their estimate for cleaning up the damage was too low. Here's another one. You know why people talk about climate change? Just those greedy climate scientists. They just want research dollars. They're making up this global warming stuff to get research dollars. Now, when you think of the greediest money-grubbing people that you've gone to school with, they're usually the scientists, aren't they? Right? That makes a lot of sense. Here's the annual budget for climate change research in the U.S., $2.6 billion. ExxonMobil profit in 1 month is $3.1 billion. Where's the financial incentive, do you think? Finally, don't believe me. Listen to what our most prestigious scientific organizations say. Because of this big climate cave thing a couple of years ago, scientific organizations felt compelled to get the facts out. So they each came out with statements. So U.S. National Academy of Sciences said, a strong, credible body of scientific evidence shows that climate change is occurring. This is caused largely by human activities and poses significant risk for a broad range of human and natural systems. The largest general scientific professional society, AAAS, American Association for the Advancement of Science, which publishes Science magazine, which along with Nature is probably, those are probably the two most prestigious scientific journals, general scientific journals in the world. AAAS came out with this statement. The vast preponderance of evidence, based on years of research conducted by a wider range of different investigators at many institutions, clearly indicates that global climate change is real. It is caused largely by human activities, and the need to take action is urgent. We saw in the boxer, Paul Simon, 1968, still a man, here's what he wants to do, and he disregards the rest. That's the situation we're in. These books are pretty good books that sort of explain why there's misinformation out there. Merchants of Doubt, Naomi Oreskes is a professor at the University of California, San Diego. It's a really excellent book. I especially recommend that one. If you want more information, go to Skeptical Science. There's an Australian in Queensland by the name of John Cook. He does a great job of compiling all the arguments and giving the peer-reviewed scientific literature responses to them. He's even got an iPhone application. I got it in my iPhone. Okay, so I'm just about out of time, so I'm just going to run through the rest. What can we do? All right, efficiency, renewable energy, coal with carbon capture and storage, nuclear. I think we need to do all these things. I'm sorry, but you can't pick your favorite because we're out of time. This is an enormous crisis. And so I work in renewable energy, and people say, Chuck, do you favor nuclear power? I say, we can't afford to take anything off the table, in my opinion. So we did a study, Tackling Climate Change in the U.S. is the one I passed around. We looked at trying to, what would it take to limit warming to 1 degree C beyond 2000? We'd have to reduce U.S. carbon emissions by 60 to 80% by mid-century, and that's probably too low. I think it needs to be more aggressive. That would mean saving 1,200 million tons of carbon per year in our emissions. So we looked at all these different, we had experts in each area and estimated, and we basically, this would be the curve to be on a path for a 60% reduction by mid-century, 80% reduction by mid-century. And we plotted out the results for each type of efficiency and renewable and looked at the carbon emissions. So if you plot them out, that's energy efficiency. That's a huge chunk. That's wind, the biggest renewable contributor. PV, concentrating solar, biofuels and biomass, and geothermal. And we're in the ballpark of where we need to be by deploying these technologies. I did a separate analysis. I want to know what's the incremental versus conventional. What is the incremental increase in cost on an annual basis between now and 2030 of these technologies? And I won't go into the details, but I wrote a paper that explains the different assumptions. But a basic life cycle cost analysis. And so if you look at, here's a wedge diagram, and this shows you, here's what the Energy Information Administration says we're going to do in terms of emissions. We're on that path. This is what efficiency can get you. And this is wind, and then the other renewables down here. And I estimated the cost. Basically, all those renewables wedges would cost us $26 billion a year. Now consider, some estimates have shown that the amount of money that we subsidize fossil fuels to the tune of is about $50 billion a year. So that's about half of what some estimates show we give fossil fuels in subsidies. It's about, we were paying about that every 2 months in the Iraq War, at the height of the Iraq War. But the good news is that this energy efficiency wedge would save about $100 billion a year. So if you really package these together, if you got serious about deploying efficiency and renewables at the same time, you'd save the economy about $80 billion a year. So that's the report. I passed it around. This is a report that I recommend you look at, a paper by Jim Hansen of Goddard. And it really says that, you know, we need to get back below 350 parts per million. The ice sheets, paleoclimate data, the studies show us the ice sheets are not sustainable above 350. Why are they melting? Because we're at 395. If it's higher than 350, they're going to keep melting. If we don't want to lose the ice sheets, and I would think maintaining the planetary ice sheets might be important, we got to get back below 350, and he lays out, you know, the measures that must be taken. This is a paper I actually work with Jim Hansen and Kutscher, who works at Goddard with Jim. And we came out with a review paper in environmental science and technology. We looked at all the options, not just renewables. We looked at coal with carbon capture and storage, and renewable and nuclear, and what the various options are for phasing out coal. And I'll leave you with this. We don't inherit the earth from our ancestors, we borrow it from our children, a quote by David Brower, and I think we need to think along those lines. And I did want to mention, and I'm sorry, I think I must have switched the presentation. I included a couple slides. There's a new study NREL just came out with. It's a Futures of Renewable Energy study. If you go to the NREL website, www.nrel.gov, interestingly, their wedges look very similar to ours. You know, that's a report worth looking at because they did very detailed modeling to look at how these various energy components compete against each other. So I recommend you take a look at that report. And I'm happy to answer any questions if we have time. Any questions? I was speaking at Colorado School of Mines a couple months ago. I always get, you know, you can't cover all the skeptic arguments, but one of them said, well, wait a minute, I read that volcanoes put more carbon dioxide into the atmosphere than humans do. And here's what gets me about those kinds of statements. And this student had read it, you know, probably in one of the websites. And I looked it up, and sure enough, this was a common skeptic argument that's been floating around the last year. And, you know, I'm thinking, can you imagine you go to the top PhDs? I mean, like Jim Hansen got his PhD at the University of Iowa under James Van Allen of Van Allen Belt fame. I mean, these are smart guys. Can you imagine you go to these and you go, hey, you know, volcanoes put in more CO2 in the atmosphere than mankind does. And those guys go, oh, why didn't we think of that? I mean, what's the chance of that, right? And these people are not idiots. The reality is the United States Geological Survey has done a study. And roughly, mankind puts in, on average, 135 times as much CO2 into the atmosphere as volcanoes do on an annual basis. So, I mean, there's just no truth to a lot of these. Okay, so anybody else got some good ones? Yeah, go ahead.
Just a quick comment to that. A couple months, years, I'm not sure ago, there was this one volcano in Iceland that broke out, and the air traffic over Europe stopped for a couple of days,
Sure.
2 weeks. And there was this estimate of how much greenhouse gases this volcano put into the air, and they compared this to how much greenhouse gases were avoided because the planes stayed on ground. And the planes would have emitted much more if they had been in the air.
Really? Okay, that's an interesting statistic, thank you. I'll try to remember that one.
Excuse me.
Yeah.
If you don't do anything, just write the scenario which is working right now.
Yeah.
In the worst scenario, how much time do we have?
Well, look, I was making the case. You're starting to see these publications now. Look, when there was a bad wildfire season, a bad drought, there was a bad heat wave in Europe that killed 30,000 people a number of years ago, and scientists would say, you know, well, this is consistent with the models. We can't say this was caused by climate change. It was the same thing when the tobacco industry was coming out with a lot of misinformation about tobacco. You might have someone get lung cancer, they'd sue the tobacco company, they would lose. Why? Because they couldn't prove that their cancer was caused by smoking cigarettes. You have to look at the statistics, okay? And so you can't prove that one weather event was caused by climate change. But the fact is, climate change is really fundamentally changing the whole water cycle on the planet. It's causing, the higher temperatures mean that the air holds more moisture. That means it has not only more sensible heat, but more latent heat. More energy means the potential for more intense storms. And so now you're starting, I tried to show you today that just in the last couple of months, we're seeing all these scientific publications come out that are finally saying, you know what? This is not normal. We can show statistically this would not have happened. The chance against that is 1 out of a million. The chance of that happening is 1 out of a million if we hadn't been altering the Earth's atmosphere. So the point is, it's already happening. All right, we're already seeing the effects. And the fact is that there's more heating in the pipeline. So what we have to do is get to the root of the problem. At the same time, I'm sorry, but we are going to have to adapt. We are going to have to accept the fact that global warming is part of what your generation is going to experience. And we have to, there's going to be some building of seawalls, there are going to be adaptation measures that we take. But look, all the serious studies that I've seen show that it's much more cost effective to get at the root of the problem and stop the carbon emissions than it is to clean up the damage. All right? So basically, what's the most expensive thing you can do about climate change? Nothing. That's the most expensive approach. So right now, the essential approach we're taking, if you look at that CO2 in the atmosphere, it just keeps going up. We're not really making a dent in it. I mean, we have things, achievements we can point to that we can be proud of. But we have a fundamental measuring stick, and that's the atmospheric CO2, and it's still going up 2 parts per million per year. We're not really putting a dent in it. Any other? Gary?
3 comments, because I was amused this morning that yet another lump of ice the size of Manhattan fell off
Yes.
today.
Yes, that's right.
So that the researchers in East Anglia, which is a very, very funny part of England,
It's the Climatic Research Unit. It's the one where the emails were hacked.
Right. Now that group had 3 independent inquiries on the released emails. And
I showed quotes from each one.
They were all those clear.
Yeah.
The people who uncovered those emails cannot be tracked. They were professionals who got in, and they had to drop all charges against anyone because it's a 3-year limit. And another one was that more people now believe in global warming thanks to our fires and our flooding. So there is it's a positive effect of having a wildfire. More people believe in.
The only issue there, Gary, is that some of the polls show that more and more people are believing that the climate is warming, but still a lot of them don't believe that we're causing it. And if you really want to solve a problem, knowing it's happening isn't enough. You have to understand what's causing it to address it. One of the things I say about, look, obviously I support renewable energy. I've worked in it for 33 years. One of the points I try to make about climate change is, sure, we want renewable energy. What climate change does, it puts urgency on the problem. That, yeah, a lot of people agree, yeah, we need to get renewable energy out there. My point is, if you understand climate change, you understand we need to do it a lot faster than we're doing it. There's an urgency to this problem that we're not addressing. And that's where climate change is really affecting, what our energy transition has to be. Yeah.
You mentioned towards the start of your talk that whether or not someone is a climate skeptic depends a lot on party lines.
Yeah.
Given that a lot of the skeptics also refuse to accept the weight of scientific evidence, what do we do given that the current political situation could change pretty rapidly, as I commit to delay things for 4 years or 8 years?
It's a scary proposition. I mean, it's, one thing I pointed out, it was something like, 66% of Republicans say that global warming is exaggerated. Well, it was 100% of Republican candidates for the presidency, right? But that's not representative of all Republicans. And I would, I think one of the things we could do is appeal to that, 30+% of Republicans that do get climate science, that maybe they have good scientific backgrounds and they understand it, and get them to be more vocal. I think one of the big impacts, to me, the biggest impact of the misinformation campaign is that not that it's convinced people that should know better that it's not happening, but it's made them afraid to talk out, to speak up. A lot of politicians, I've had a congressman come up to me and say, I'll talk about energy efficiency, I'll talk about job creation due to renewable energy, I will talk about energy independence. I'm not going to talk about climate change because I know I'm immediately going to alienate a good portion of the audience. And so this fact that people are afraid to talk about climate change, that's why I called it the elephant in the living room at the beginning. It's there and people are afraid to talk about it. And look, we're not going to convince everybody, but you don't need to convince everybody to take action. Mike?
A lot of this, for example, fossil industries, these energy companies, they're all in a state of denial, we say. If you look at most of them, you see them preparing for the day when they're going to have to just knuckle under it.
Yeah.
And so I think even believing any political polemic today is you're just listening to nonsense. It's really professional noise. I mean, they're doing
Sure.
It's called dissembling, and that's how you just break up an argument by just screaming loud and crazy stuff. So all that stuff is kind of meaningless, especially with the last few political cycles. And ever since Newt Gingrich, that's their ploy. It's just a ploy. But it's just, I think it's just as important that you make sure that the believers, people who understand don't over-interpret. It's just as bad for them to over-interpret as skeptics do for their years. And one question I have had for a long time is all these issues about these glaciers. And there's two ways you can knock out a glacier. One is you can warm it up, and the other is you can cover it with soot.
Yeah.
The Indian glaciers, it's very clear. That's the haze from the cities floating up there. My question on the Arctic
Yeah.
ice, how much of that is going to be Chinese aerosols or industrial soot or other things that are not climate change as we classically define it, but are a product of the industrialization and use of fossil fuels. So how do you keep a handle on those things to make sure we're not leaving out other interpretations?
But that's an excellent point, and certainly there have been a number of studies that will argue that in the case of the Arctic, deposition of black carbon from burning of coal is a major contributor because it basically reduces the albedo. All right, and so less energy gets reflected back. There was a study by Hansen that I think concluded that a third of the warming in the Arctic, I think that's the right number, was due to black carbon deposition. And so I didn't cover it here, I can't cover everything, but there have been some studies indicating that if we can address the black carbon problem, we'll have the quickest return on our investment. So I do think that cleaning up emissions from the standpoint of black carbon would help a lot. But again, we still have this issue of CO2 being dissolved in the oceans, and there are various studies as to when it's really going to be critical in terms of coral life and that sort of thing. So for that reason, we also need to reduce CO2 emissions. And again, I think the studies show that the greenhouse effect is still larger than the carbon black deposition effect, although it is important in the Arctic. Yeah.
So I had a question actually. You said that one signature of the fact that it was a greenhouse gas effect was that the lower atmosphere was warming and the upper atmosphere was cooling?
Yeah.
Could you explain why that happens?
Just because you have carbon dioxide going through the atmosphere, and you have the Earth radiating heat away. Okay.
Yeah.
And so the lower that carbon dioxide that's been added low traps that heat further on down. One of this is.
So wait, but I can understand why the lower atmosphere would warm more, but they should still both be warming, right? And the graph you showed that it was actually going down in the upper atmosphere.
No, actually, the lower atmosphere can actually block heat from that would have gotten to the upper atmosphere.
Okay.
And also, the actual troposphere, I believe, is changing position. One of the issues is that one of the skeptic arguments I didn't cover is that the skeptics say that it doesn't take much CO2 to basically absorb all the infrared. So if you add more, what difference does it make? Well, the difference it makes is what happens is you add CO2 to the atmosphere. The atmosphere isn't just monolithic. It's a lot of different layers, okay? And so what happens is the CO2 in the lower part absorbs infrared radiation. It has to radiate back up, so it re-radiates. And so you have sort of think of a resistance, thermal resistance network of radiation going on from one level to another, okay? And essentially, what it does is instead of emitting out to space from a low level through a transparent atmosphere, it has to work its way up, and it starts emitting out to space from a cooler part of the atmosphere, all right? And the cooler an object is, the less radiant heat it gives away. So that's basically causing the Earth to look cooler from a distance and therefore radiating less heat away to space. So that's another way to look at that problem. The other answer to the skeptics that say CO2 should be saturated is, look at the planet Venus. I mean, Venus is a lot hotter than Mercury, and Mercury is closer to the sun. Venus has a very thick cloud cover which reflects away a lot of sunlight, but it's incredibly hot. Why? Because it has so much carbon dioxide in the atmosphere. So if the saturation argument had any validity, Venus would not be anywhere near as hot as it is. Yeah?
You mentioned several positive feedback loops capable of runaway. Which one of these keeps you up at night? If there's one that's worse than the others.
Well, you know, certainly I think that the possibility of releasing methane from the permafrost and also methane hydrates in the ocean, there's a lot of concern about that one, that it could be a sudden pulse of greenhouse gas into the atmosphere. And apparently there have been times in history when those pulses have occurred, and they don't totally understand them. But you know, one of the things that I should be careful about here is and I have to be careful not to oversimplify the problem. There are a lot of things we don't understand the details about. But the scary thing is we're conducting this enormous experiment. We've taken a fundamental infrared absorbing constituent in the atmosphere, all right? And we've greatly increased it. Like I said, it's gone up 25% just in my lifetime. And we don't know exactly what's going to happen to the weather all around the world. All we know is we're screwing it up, but we don't know how bad the impacts are going to be. And that's really scary to go into this very uncertain realm that we're entering. So yes, there are uncertainties, but the fact is, it's very well known that adding greenhouse gases to the atmosphere causes the Earth to warm up, and that has significant impacts on the weather and the climate. Yeah.
So one thing that kind of freaked me out in your slide was the slide showing skepticism on climate change by a political party in the U.S. There was a distinct spike in 2004,
Yeah.
election year. Have there been studies on how political an issue is around the world in various countries and how belief is affected by political events?
I think so. I mean, the U.S. is pretty unique. This sort of misinformation campaign has just gone gangbusters in the U.S. Now, there are some people, and Gary could probably tell you this, there's this Lord Monckton in England. I mean, there are certain, very conservative people in England that fight this too. But throughout most of mainland Europe, certainly, and even in England, most people get it. They get it that, greenhouse gas, we're emitting greenhouse gases that's causing warming of the planet. But there's a very effective misinformation campaign in this country. And it doesn't really take much money, What happened, well, companies have taken money and sent it to a whole bunch of different corporate think tanks, all right? And they come out with all these reports, and so it looks like there's this real plethora of people out there debating it, all right? But it's sort of a technique. It's taking small amounts of money and spreading it around. And it's very effective. And like I say, I mean, different people, get their news from different sources. If you watch Fox News, you're going to get every day the latest joke about about climate change. And so if you're the kind of person that watches that every day, it's hard not to be influenced by that. So it really, I think, to me, that's one thing. They say that the people that are disseminating misinformation about climate change are using the same tactics that the people in the tobacco industry use. Actually, it's not just the same tactics. In some cases, it's the same people. Right? So if you go, there's a website called Junk Science, and there's a guy named Stephen Malloy who runs it. What did he do 15 years ago? He worked for the tobacco industry. Oops, lost my microphone. He worked for the tobacco industry, arguing that secondhand cigarette smoke is safe. okay? And now he's changed to a different career. But to me, I don't recall, I mean, I'm old enough to pretty well remember the tobacco days. And like Mike said, the tobacco industry did what you see the energy industry doing to a certain extent. You know, the big tobacco companies, they bought up Nabisco, and they diversified into other fields. They saw the handwriting on the wall. They weren't dummies, okay? But the one thing they didn't do is, I don't remember there being this incredible political schism, you know, between, you know, where one party just totally said, oh no, tobacco smoke's fine. I don't remember a party saying that. So the fact that they got to a point in today's politics where, I mean, you can't run for office in the Republican Party if you come out and say, boy, climate change is a problem. I mean, it's unacceptable. So to me, that's, I mean, I have to begrudgingly give these guys credit to pull that off. I mean, that's amazing to get a whole, you know, spectrum. Now, like I say, if you look at what Republicans think in the Gallup poll, there's certainly still plenty out there that get it. And you know, maybe those people will become more vocal. We can certainly hope. Yeah.
I would just quickly like to comment that, especially this political thing, I guess it's a very American specific thing.
Yeah.
I don't know, in some countries where I know the politics is better, like Germany or some other European countries, I'm pretty sure that a major politician will run around and say, oh, climate change is not happening, would be laughed at and kicked out of office.
Yeah.
It's just, I think it's a very American thing, this whole...
I think it is. I think you're right, yeah.
problem.
You want me to explain that? I'm not a sociologist, I'm an engineer, so I'm not sure I'm the best person to explain it. But yeah, I mean, we see that. And I do think it's just because of all the money that has been invested wisely. I mean, these people know how... Look, I mean, where's the most advertising? I mean, when you think of clever TV commercials, I mean, there's a lot that are produced in the US, right? And so these people are good at getting a message across. They do focus groups. A lot of money gets invested on putting focus groups together and finding out, you know, how you get through to people a certain message. These people are very good at messaging. And so if they want to get out the message that, you know, climate change isn't happening, they know how to do it. The real message is doubt. What they're trying to do is they're trying to seed doubt, and that's why Naomi Oreskes' book is called Merchants of Doubt. You're trying to make people doubt the science. And again, it's people are just very good at messaging.
Please move on. Thank you, Chuck.
Okay.